Hello and welcome to the Consilium Aquis Sulis Introduction to Automatic Train Operation, part of our series on train protection and automation. This course is intended for transportation engineers, operators, consultants and managers and consists of a single online video presentation which can be viewed at will. Please note that the course is for educational purposes only. Please consult the applicable standards for definitive information. There are no prerequisites to attending this course. However, it is advisable to view the corresponding videos on train protection and cab signaling before doing so. This video will answer the question, what is automatic train operation? It will then outline the different grades of automation before explaining the motivations for and challenges of automatic train operation. Finally, it will relate automatic train operation to automatic train protection and cab signaling. In automatic train operation, trains are driven automatically rather than by a human driver. A driver may still be present to perform specific functions, such as closing train doors and confirming that it is safe for their trains to depart from a platform. The driver may also intervene in failure and emergency scenarios. However, the driver does not drive the train between stations in normal operation. ATO is defined at different grades of automation, from 0 to 4. These reflect the extent to which the driver, or other railway staff, still needs to perform specific functions and intervene in failure and emergency scenarios. In GOA 0, trains are driven on-site by a driver at a speed from which they can stop, in the distance seen to be clear. GOA 0 is the normal mode of operation for road vehicles, but in railways it is mostly limited to sidings, depots, and degraded mode operations. In GOA 1, trains are driven by a driver in accordance with conventional signaling or cab signaling. Generally, this is accompanied by some form of train protection to mitigate the risk of driver error leading to a train traveling further or faster than authorized. GOA 1 is the normal mode of operation for mainline railways. In GOA 2, trains are driven automatically. There is still a driver in the driving cab to close train doors, confirm that it is safe for their train to depart from platforms, and drive in failure and emergency scenarios. Typically, GOA 2 railways include planned periods of manual driving, GOA 1, to maintain driver competence. Many metros operate at GOA 2. GOA 3 is similar to GOA 2, but unlike GOA 2, it has a train attendant on board each train in lieu of a driver in the driving cab. The Docklands Light Railway in London, UK, operates at GOA 3. In GOA 4, also known as unattended train operation, trains operate without any member of staff on board. GOA 4 railways typically have platform screen doors to prevent incursion of passengers and other obstructions into the path of trains. They generally have evacuation walkways alongside the track so the trains can be accessed and evacuated in failure and emergency scenarios. They usually also have direct communications between onboard public address systems and control centers so that controllers can speak directly to passengers in failure and emergency scenarios. Some modern metro lines and airport shuttle services operate at GOA 4. The motivations for ATO are similar to those for connected driver advisory systems. However, the potential capacity, service regulation, and energy use benefits are greater for ATO as it has direct control of train speed. Further benefits can also be realized when ATO is implemented entirely unattended by railway staff, as vehicles can be stationed at strategic locations without the need for staff at those locations and brought into operational service when required. ATO offers capacity benefits because it enables trains to be driven with a consistent driving style characterized by rapid deceleration and acceleration. Trains can be driven closer together, thereby increasing capacity, particularly where there are frequent platform stops, as in metros. Further capacity benefits can be realized through the ability to regulate train speed precisely and dynamically. For example, if two trains are expected to arrive at a converging junction at the same time, one can be made to slow down and the other to speed up, so that they follow each other as closely as possible and flow seamlessly over the junction. Similarly, on plain line train speed and station dwell times can be regulated to even out gaps in services or ensure adherence to timetable. ATO, like connected driver advisory systems, can also regulate speed to reduce energy usage, wear and tear. ATO offers further benefits when trains operate entirely unattended by drivers or other railway staff. This provides the operational flexibility to run train services unconstrained by the availability of staff at their stabling locations. Trains can be stabled in strategic locations, ready to operate services at short notice, regardless of how accessible those locations are to staff. Whilst ATO offers many benefits, it also entails challenges. It places an even higher level of dependency on the signaling system than manual driving, as it has direct control of train movements. Although a driver or attendant may intervene if ATO behaves in an unsafe manner in GOA2 or GOA3, this is contingent on them noticing it in time. In GOA4, there is no one on board the train to intervene. The consequence of this high level of dependency is the challenge of ensuring safety in all reasonably foreseeable scenarios. This depends on the safety, integrity, and availability of the signaling system itself, as well as on other mitigations in place. These may include platform screen doors, intrusion detectors, and operational procedures to ensure that lines are clear of people and other obstructions when trains are operating. They may also include walkways to access and evacuate trains in failure scenarios, direct communications between on-board public address systems and control centers, low operational speeds, and protection from the elements. A further challenge of ATO at GOA 2 and GOA 3 is managing driver or train attendant under load and overload. In normal operation, the role of the driver or train attendant is very limited. Hence, there is a risk of boredom resulting from lack of stimulating activity. However, in failure and emergency scenarios, the workload can increase very suddenly, as the driver or attendant then has a complex situation to deal with. Much of the functionality required to drive trains automatically is provided by cab signaling technologies. ATO technologies typically include additional functionality to regulate train speed and station dwell times, and to skip or stop at specific stations. However, the main differences between cab signaling and ATO arise from the greater dependency placed on ATO. ATO directly controls trains without the intermediate sense check of a human operator who may detect anomalous states, and in GOA 4 may not even be present to intervene. ATO needs to ensure there are no people or other obstructions on the line. ATO needs to calculate safe braking curves according to adhesion conditions, whereas in cab signaling, drivers can modify their driving style in low adhesion scenarios. In GOA 2, ATO needs to engage and disengage in a manner that is intuitive for the driver. In GOA 4, ATO needs to handle a wide range of failure and emergency scenarios. Although they have some overlapping functions, ATO systems may be deliberately separated from ATP systems to reduce the scope for single points of failure leading to unsafe states. ATP can thus continue to fulfill its role of intervening if a train travels further or faster than authorized, regardless of whether controlled by a driver or ATO. In summary, in automatic train operation, trains are driven automatically rather than by a human driver. There are different grades of automation defined, from GOA 0 to GOA 4, according to the extent to which a driver or attendant still needs to perform specific tasks. ATO enables capacity improvements by driving trains with a consistent driving style and regulating speed through junctions. It can also offer better service regulation, reduced energy usage, and, when implemented as unattended solutions, greater operational flexibility. A key challenge of ATO, particularly at higher grades of automation, is ensuring safety in all reasonably foreseeable scenarios.